Okay. Okay. We were going through yesterday the broad understanding of different problems what we solve in machine learning. As we discussed it just now, there are supervised learning problems, unsupervised learning problems, reinforcement learning problems. The goals are different for each of these three. Now we concentrate in this discussion mostly on supervised learning basic algorithm that is called linear regression. That is also with one variable. We'll come to know that what is linear regression, what are the variables we use, what is one variable linear regression means, all those things. So as I told you, in prediction, there are two types of predictions. Either you can predict a class for a given object, or you can predict a number, real number that with these parameters, what is your prediction it will attain. So regression is of the second kind. So we will predict a real number here. We are not going to predict a class. In regression problems, we are taking input variables and trying to fit the output onto a continuous expected result function. Univariate linear regression is used when you want to predict a single output value y from a single input value x. So in univariate or with one variable linear regression, we will have only one explanatory variable. That is also called independent variable. There is nothing prediction for that. Those things will happen naturally. So when those things happen, then correspondingly dependent variable, that is called here y, or response variable, what it may take value when these natural phenomena happens. So that is the thing in univariate linear regression. Only one input variable, one independent variable versus one dependent variable. So linear regression attempts to model the relationship between two variables by fitting a linear equation to observed data. So you know that a linear equation means it should have only powers of 1 maximum. That is called linear equation. So x and y, x is independent variable, y is dependent variable. Y should be written only by using constants and x up to some multiples or constant multiples of x plus some constant. Only that much. Or else you can say that it's a line equation or linear equation that shouldn't have anything more than power 1 in that equation, that is called linear equation. If you can explain y only by using x power 0, that is constant, or x power 1, then it is called the relationship between x and y is linear, because we are not using more than power 1 terms. So that is assumption. We don't know that whether the data set is actually providing us a linear relationship between x and y. But one assumption we are making in the beginning, okay, if there is a linear relationship, then what is this linear relationship? We are trying to find that, if at all, if it is there. Later on, we will see that if there is no linear relationship, then whatever parameters you use to predict y based on x, you won't get close values of y in reality. Then we will find out that there is no linear relationship. Or else, you can also plot the data and see that whether x and y are the points when you take X and Y points, are they falling on a line or not, or close to a line or not? If they are falling on a line, then you can see visually there is a linear relationship. If they are not falling on a line, then they don't have a linear relationship. For example, a modeler might want to relate the average temperature of a region to their rainfall. So they collected the data for so many years, day to day. Then their temperature they got, that whole day temperature average. Then which days the rainfall, how much it happened. So that is the problem. They want to predict rainfall based on average temperature from the collected data. Collected data is our experience. Target is predict how much of rainfall will happen. Performance is it close to the already observed values in the history? That's all. Let's see. That is what we try to do now. So the data set will be given like this: X values. So average temperature that day was 35, then rainfall was 40, 25, 30, whatever that it is given. You think that on this particular region, there may be daily or every day it may rain, something like that. It looks like that here. Even in 35, 40 degrees, it is raining, and also 25. Whatever that it is, we can think that this as a not a real data. Maybe it's for the purpose of the example, we are taking this data. Then you can simply use Python code here to fit a linear regression. So for that, we will use these libraries. sklearn or scikit-learn is also called. There is one famous library, but I heard from your placement officer who are to get job. They're also asking other libraries you should be well versed, like TensorFlow, other things, Keras. So you can also try those also when you practice these algorithms in Python. Of course, the course is given in Octave. That is up to you whether you continue with Octave. If you want to get a certificate, if they allow. I heard that it's, they are not giving free certificate. Then they might not be giving. During COVID time, they were more considerate. Then it is your wish whether you do with Octave or whether you do with Python. I also gave a resource. Somebody worked writing code in Python for those assignments and all explanations what they gave in this course. In what is that platform? In Slack. Slack, I put that link. So now you are taking that NumPy, that Introduction to Data Science. We discussed what is NumPy. NumPy, it is an array. Array concept was not there in Python, but through NumPy we are getting that. So you are storing X in an NumPy array, Y also as NumPy array. Then there is a library function called linear regression. Then we are fitting for X and Y. Then we are getting some parameters. All those things you can try and see that you'll get a linear regression fit for this data. Okay. So what theoretically it does is, on a space of 2 dimensions, because we have only 2 variables here, X and Y. If you plot these points, so the lowest X is 15 and its corresponding Y value is 25. So 15, 25, this is 1 point here. Where is annotation option? Yeah, disable annotation.
So while you're on present mode, you cannot annotate, sir.
Sure, I got this annotate symbol here.
So once try to check view options.
Yeah, it is not coming. You are right. Okay. So this the first point, it's from left to right. You see this is 1525. Then this is 20. You can see from table 20 is attached to 28. Then 25 is attached to 30. All those points are put it here. Then we want to find out a line. First of all, can you see there is some linear relationship between x and y? Can we put all these things with respect on a line, all these points? Can we draw a line so that it's all these points fall on that line?
One single line cannot pass through every point, but we can.
But varying slope can make it, I guess.
Okay. So, but anyway. So it is not a perfect linear relationship. That is what we can find out, right? By looking at the data. So you cannot get one line which passes through all these points. So that is for certain. All of us know that little bit geometry. So one line is defined by only 2 points. So you cannot put all these points and get a line unless they have the same slope. So here, what is happening, we cannot find a line, but we are interested to, of course, let's say if we don't have any other mechanism to get a relationship of y with respect to x, and we are only interested to see that linear relationship, sorry, we should get a close line, or we should get a line which is close to all these points. Okay, so which is close to all these points. How do we get a line? Then there may be different things. So if you see here, so your points are something like this. Then we are drawing a line. Somebody may say this is close, or somebody may say this is close, because the first point is close to this point and this point, right? The first line. And the second line is close to this point, but this also close to this point, but far from these two. Maybe somebody may say this is close, or somebody may come up with say another line. This is close to all these points. So we want to get a line which is close to all these points. Then the question comes that how do you determine that it is close to all these points? You can say that you can start actually passing through, then definitely it is close to this point. There is no doubt. But remaining points are not close enough like this. Then the question comes that it's okay. I'm not interested 1 point is close or 2 points are close to that, or how many points are close to that line. Putting all the data together, I want a line which is close to all points in terms of the average distance it is deviating from that line. So if there are 100 points, then what I do is I take how much it is deviating for each point in 100, then I'll average that. That average should be less. That is one way of getting a line which is close to all the points. Okay. Then there is one more problem will come when you are taking average. The deviation, the line which you see here, some line is given. There is deviation at 15, the y value should be how much? 25. But if it is on the line, suppose, how much it is deviating from the line? The y is the vertical axis. So vertical distance you need to see. It is somewhere
Almost 0.5, sir.
22, right? The
Yes,
line 15 is falling at 22. But the original value of y is what? What observed value is 25.
25.
So it is deviating positive 3, means 3 more than the line. So what is the deviation at point 20? Not much deviation, right? It is
exact.
not the line. What about at 25? It should be something like 30, but it is not at 30, it is maybe 28. So it is negative, so -2. So when you are averaging like this, there are some positive changes, there are some negative things. So all those will cancel. Then if you take average, then average distance may become 0 also sometimes. But will that be good? Are we predicting correct if you do like that? No, because we are making mistake here also, because this cancelled this positive to negative. That doesn't mean that we are predicting at 15 and 25 right. We are actually predicting a wrong values. But only these 3 values are there. This is positive deviation, this is negative deviation. If you take average, then positive deviation, negative deviation will cancel. We'll get average deviation is 0. That doesn't mean that they are not making any mistake, this predicting. So that's why we should have some positive notion of deviation, not in direction we should take, whether it is positive direction deviation or negative direction deviation. In whichever direction it deviates, that should be taken as a deviation. Then one method is you consider mod of value, whether it is positive, negative, you'll get always positive. Then other way is, okay, you consider square error, whatever positive error or negative error, if you make it square, then always it becomes a positive thing. So then you are magnifying the error, but you always get a positive error, whether it makes a negative error or positive error. So that is what 2 methods we can have to make it not cancel the positive errors and negative errors, so that we will get a 0 error sometimes, or that doesn't show any good indicator for us how good the algorithm is working. So the question is now, what can you change to change this line? Because this line, okay, once we get this line, then we can find out what is average squared error or average modulo error this line is making with respect to y values. Okay, we know that now. But how do we draw different lines and get error for each line and get a line which is making less average squared error? Suppose if we fix for the square error. So that is the now problem in front of us. Now we know that the equation of the line is y equal to some constant. You might have seen c plus mx, or famous equation is mx plus c. C is constant, m is the slope, x. So here m is as you change m and as you change this constant, this is 4.60 is constant, 1.14740 is the m. So this particular fitting in linear regression is giving this line, and this line is supposed to be close than any other line in a squared error deviations. But if we want to change this line and see that how much that line make error, what we can change in this equation and change this line? You cannot change observed x values, right? So what can you change then?
M and C.
Constant term and slope term, or a constant of x. Yeah, this one coefficient, x coefficient. So you change x coefficient and constant. So here, if you see, the equation is written something like here. Still, it is not. Where is that equation? Yeah. So we got forward. So the equation is written here, h theta x means theta is the parameter. Theta we are writing as a tuple. Theta contains theta naught and theta 1 values. So you change the tuple with different values for theta naught and theta 1, you will get different lines. So the hypothesis function for univariate linear regression is the general form of an equation of a straight line, h theta x equal to theta naught plus theta 1x. We find the best h theta x values for theta naught and theta 1 to get our estimated output y head. So when we use this theta naught theta 1, once we fix, so we should be sure that those theta naught theta 1 are giving close values than any other line or than any other pair of theta naught theta 1 to the existing values of y in that training data set. So I may use many times this training data set and test data set. Training data set, already we know what should be the output. Training data set. Test data set, we may not know, or we might not have used the output to fix this, to find these parameters. They are called test data set. Anyway, when we deal with the linear regression, we will come to know that. See what is test data set, what is training data set, how do we divide. Now, you assume that a given data set, x and y values are given. We need to find a line with the parameters theta naught theta 1 so that it optimizes squared error deviations. In other words, we are trying to create a function called h theta that is trying to map input data x's to output data y's. So for example, of relating the average temperature of a region to their rainfall using a linear regression model finds this equation it found means theta naught value is 4.60 something and theta 1 value is 1.14. If you want to, you can try this code and see that it's exactly you'll get this equation. So now the question is, how are you getting this theta naught theta 1 so that they optimize your squared error deviations? Initially, we do a random guess for theta naught and theta 1. So we don't know which theta naught theta 1 will give us the good fit. So we randomly take theta naught theta 1. Then we will use some mathematics to find good theta naught theta 1 so that gives good estimation of y. So let us take theta naught equal to 2 and theta 1 equal to 2. So initially we will assign random values. Usually in most of the algorithms they put 0 zeros, but we are assigning some random values. You can still do that. Then h theta x, our equation is theta naught plus theta 1x, 2 plus 1.2x, and estimated output would become y equal to 2 plus 1.2x. Now we have x value, y value. If we want to predict y values based on this equation, then what values we'll get, we need to see now, and how much errors they are making. Okay, now your x value is 35. Observed value for that x is 40. Then you put 35 because x y predicted. This is called hat. Y hat is always called y predicted here in this lecture. So y hat, how much for x equal to 35?
What?
How much it is? What is 35?
44, sir. 44.
Here it is written, right?
2 plus 42. Sir.
So similarly, for x equal to 25, what is y expected or y estimated? 30.
Substituting that values, will be getting this 32 and 26 from this.
Yes. Okay. Then how much of error it is making? The first one?
4, sir.
Minus 4.
Negative.
Yes.
But we don't want to consider them negative, positive, right? We have seen they will cancel and we will get a wrong signal that it is not making mistake. So you make it positive error. Means modulo you take. The first one is making 4, the second one is making 2, like that. So what is average error here?
10.
10.
Then 4 plus 2 plus 5 plus 4.4 plus 10 divided by all how many values? 6 values. That is the average error. Average modulo error or average absolute error it is. So there is some problem to consider absolute error. I will discuss that. That's why we will move to the squared errors. So for input of x equal to 35, to our hypothesis, y hat will be 44. This is off by 4. Let us try out various values of theta naught and theta 1 to find values which provide the best possible fit or the most representative straight line through the data points mapped on the xy plane. Now you change theta naught theta 1, find out like this, then draw that line see that it's how that line looks, how close it is, all those things you can try. So how do we measure hypothesis function is good. So which theta 1, theta naught, theta 1 is giving good estimate. How do we measure that? We can measure the accuracy of our hypothesis function by using a cost function. So the terminology, deviation, all those things, they are putting into a cost function, a new term they are using. See, as I was using deviation, how much it is deviate. Means how much of mistakes it makes, that is costing you, right? Means in some terms, costing means it is damaging you. How much it damages if you use that equation. That is what we should get. So which equation or which line gives less damage, we should find that line. So we can measure the accuracy of our hypothesis function by using a cost function. What is cost function? We'll decide now. Cost function takes an average of squared errors of all the results of the hypothesis with inputs from x's compared to the actual outputs y's. So right side you can see table. Original input is, our actual input is actual output is 40 for input 35, but if we use this equation, we are getting 44. Similarly, actual is 30, predicted 32. Actual is 28, predicted 26. Actual is 25, predicted 20, like that. So it is costing all these. We are not getting close values, means exact absolute values. We are not getting close to these values. So each line will give us some cost, means it is damaging our estimations. Let m be the size of the training set. That is nothing but how many instances you are giving for a training set. Then this cost function they are representing in terms of the j. So cost function, x and y you can't change, only theta naught, theta 1 you are changing. So for different theta naught, theta 1 uses, what cost you are getting, we are writing here in terms of in mathematical equation, that is 1 by 2m sigma I is equal to 1 to m h theta xi minus yi. This is absolute deviation from the actual value to predicted value. Then you are summing up all those things. Then you are dividing by, of course, there is a mistake here. 2 shouldn't be there. There are m points. So m absolute deviations, sum them, then divide by m. Then you will get average absolute error for each point. That is one way of writing cost function. Other way of writing is 1 by 2m I is equal to 1 to m h theta xi minus yi whole square. As I told you, it's a take the deviation whether it is negative or positive. When you make square, that becomes anyway positive. That's why we will take not exact values positive, negative. We will square and add them. There are m points. So then we should divide by m. There is a specific advantage by using 2m in the denominator instead of the m. So I'll discuss that later when we get derivation, this optimization of j theta naught theta 1. Why don't we use the first one, absolute errors? So to minimize or optimize this j theta naught theta 1, here the goal is minimize the cost, right? J theta naught theta 1 means the spared error should become less, or absolute errors should become less. Then you might have remember, it's in your intermediate mathematics calculus, you might have seen find the optima of a given function. Then you will find out it's a critical points for that function. I don't know how many of you remember. Then first you should find out derivatives. First derivatives equal to 0. They are called critical points or optimal points, whether they may be low or high. When you take the second derivative and substitute those points, if you get positive, then that will become a minimum point. If you get negative, that will become a maximum point for that function. So then maxima, you might have seen it, find maxima, minima of a given function. So here the function is parameters are theta naught theta 1. So we should, to apply that mathematical formulas, we should apply derivatives of j function with respect to theta naught and theta 1. but all functions are not differentiable. Particularly this mod function is not differentiable. So that's why we cannot apply directly mathematics to optimize cost function if we take the first one. But x square or anything square function is a differentiable function. Mod x is not, but x square is a differentiable function. So that's why we will take the second one, j theta naught theta 1, because it is easy to optimize by using mathematical thing. So why we are writing 2m instead of m? Because when you take the derivative of x square, 2x will come, that 2 and this 2 will cancel, so that we'll get a nice thing. Whether you optimize theta naught theta 1 based on the 1 by 2m of this function or 1 by m of this function, for the same theta naught theta 1, you will get the optimum. You won't get it, see, optimum for different theta naught theta 1 if you use 2 or if you don't use 2. This quantity may change 1 by 2m, whatever. But our interest is not finding this quantity. Our interest is finding theta naught and theta 1 for which the value we will get less. So if your scale is big, then you may get big. If you don't use 2, then you may get big and small, whatever that it's the quantities. But the quantity we are not looking. We are looking at which point you will get for this function minimum value. So that won't change whether you use 2 or not. That's why mathematically it becomes convenient for us. That's why we are writing instead of 1 by m, 1 by 2m. So not much you need to worry. Even if you remove that 1 by 2m also, no problem. But there are m points, so it is easy to explain. Average error, otherwise it will magnify like anything. This function is otherwise called the squared error function or mean squared error. Mean is nothing but average again. So we are averaging, that's why it is called mean squared error. If you don't average, this will be called simply squared error. The mean is observed as a convenience for the computation of the gradient descent, as the derivative term of the square function will cancel out 2 in the denominator. Whoever knows mathematics, they know that it's a x square derivation will come as a 2x. So 2 will cancel. Only for the convenience we are writing. We are not changing theta naught theta 1 based on this. So we will get whether you use 2 or not, same theta naught theta 1 as the best fit line parameters. So now we can concretely measure the accuracy of our predictor function against the correct result we have, so that we can predict new results we don't have. So once you can find theta naught theta 1, then you can have some confidence that you're predicting the close values. If we try to think of it in visual terms, our training data set is scattered on the xy plane. We are trying to make straight line h theta x, this line, which passes through this scattered set of data. So our objective is to get the best possible line. The best possible line will be such so that the average squared vertical distances of the scattered points from the line will be the least. In the best case, the line should pass through all the points of our training data set. In such a case, the value of j theta naught theta 1 will be 0. The cost will be 0 if all the points fall on the line. That is the ideal case. We may not get ideal case because our data, if it is not linear, then we will not get this ideal case. We need gradient descent to estimate the parameters in a hypothesis function so that it fits well into the data. So as I discussed, some mathematical techniques we will use. You already know them, even in BTech mathematics, intermediate mathematics you did. If you want, you can go through some Khan Academy videos, how to get maxima, minima of given functions of one variable, then multivariables. We are in a multivariable situation because we have 2 variables, theta naught, theta 1. So imagine that we graph cost function of our hypothesis function based on its fields, theta naught, theta 1. So what we do is, we'll take theta naught and theta 1, then we'll compute by predicted values, we'll get the mean squared error. For each theta naught, theta 1 by changing, we will plot them on a space. Then we will see that for which theta naught, theta 1, you are getting less mean squared error. We are not graphing x and y itself. we are not graphing now x and y. We are graphing what is the error for theta naught, theta 1 you are getting. So what are the variables here? Theta naught, theta 1. So you are graphing theta naught in one direction, theta 1 is other direction. So not in xy, original xy values, we are plotting theta naught and theta 1 here. So once theta naught, theta 1 is given, what is the squared error that we are plotting now? So we put theta naught on the x-axis and theta 1 on the y-axis with the cost function on the vertical z-axis. The points on our graph will be the result of the cost function using our hypothesis with those specific theta parameters. I'll show you that. We will know that we have succeeded when our cost function is at the very bottom of the points, the very bottom of the points in our graph. That is when its value is minimum. So your theta naught, so you are changing your theta naught to 0.9, 0. Whatever that in this direction, and theta 1 in this direction. Then once you get a theta naught, theta 1, you know how to predict the values y equal to theta naught plus theta 1x, then get the values, then compute the error. For that theta naught, theta 1, you are getting this much of error. So by changing theta naught, theta 1, you can see you are getting different errors. At some point, the error is very high. At some point, the error is low. So your goal is the error should become 0, right? Just j theta naught, theta 1. It is a 3-dimensional figure. One direction is theta naught, another axis is theta, another axis is j theta naught, theta 1. So in normal setup, x, y, z, this z is representing the error, j theta naught, theta 1. This is computed from the previous equation. 1 by 2m sigma of j is equal to 1 to m. Y theta minus y theta y real values whole square. From that formula, we are getting j theta naught, theta 1. So for each theta naught, theta 1, computed j theta naught, theta 1, we are plotting on a 3-dimensional figure here. So for different theta naught, theta 1s, you are getting different errors. So z-axis, let's say how much of height from the xy plane in vertical to z-axis, you can see that is the error here. Now our goal is you should get theta naught, theta 1 so that it makes less error, means it is almost falling on the xy plane or theta naught, theta 1 plane in this. So we will take the derivative, the tangential line of our cost function to find theta naught and theta 1, which will give minimum of cost function. So j theta naught, theta 1 is a function based depending on theta naught, theta 1. So we should get now derivatives of j with respect to theta naught, theta 1. The first derivatives, you will get two equations, solve them for 0, then you will get roots for that equation. Use those roots as the minimum or maximum for that. But anyway, in this case, always you'll get minimum, you won't get maximum, because you can always make a bigger line or a very far line from the existing line. The only question is how you can close. That's why you will get only minimum here, not maxima, if at all, if you have those roots for the first derivative equations. The slope of the tangent is the derivative at that point. So what is this derivative? Derivative geometrically says that the slope of the tangent at that point. And it will give us a direction to move towards. So I'll show you that it's if you get the tangent, then you will come to know that it's in which direction if you go, then you will get minimum. That it will suggest us to move in the right direction or left direction to select the correct theta naught values or theta 1 value. We make steps down the cost function in the direction with the steepest descent, and the size of each step is determined by the parameter alpha, which is called the learning rate. So if you see, this is the 2-dimensional cost function, suppose. So you have only one variable, so that is your W. Some people will also use, instead of theta naught, theta 1, weight function. Weights they are called, that's why they are representing here as W. Don't worry about it. So thetas, Ws, we may use interchangeably. This picture is taken from the internet, that's why we haven't changed it to this theta. So this is only one variable. If you have, your equation is something like y equal to theta 1x. Then your theta as changes, then you find the cost function, the cost is changing like this. So if you see here 1 point, then if you get the tangent here, then you will come to know that at this point, in which direction if you move, you will get the function value less for the next iteration. So we make steps down the cost function in the direction with the steepest descent, and the size of each step is determined by the parameter alpha, which is called the learning rate. So here we know that first we might have taken some random initial value here. So when you take random initial value, you can see here, actually you should get this yellow thing, right? That is the lowest cost function we should get by using theta, by using correct weight. But we don't know what is correct weight. We started randomly at some point, but we are here now. Now find here derivative, or that also will give you tangent. This tangent says that if tangent equal to 0, then that will become minimum function for that. So here tangent is not 0. So it is in this direction. So you move in the tangential direction, negative to the tangent. So how much you need to move, that will be dependent on your tangent. So what you need to do is initially, when you are taking this learning parameter, that is nothing but step size also, how big step you want to put. Initially, you may put bigger steps. What happens, once you close to this, means next time random initial value, we will come here and we will get here. Then next time we will fall into this line. Next time we'll fall here. You can see the step size. How much you are moving, or you are increasing your W value. Initially you are increasing more. Later on you are making small steps. Otherwise, what happens? After coming over here, if you take a big step, it may cross over the yellow thing and you may miss the minimum. So that's why learning parameter that decides how much you need to move in the tangential direction to get the minimum. If you take the bigger parameter alpha, then you may miss your yellow point and you may oscillate here and there. If you take small alpha parameter or learning parameter, what will happen? It will take more steps to reach here. If you make small steps, then it takes more steps. So it will become more computing intensive. So that's why this alpha, what they do is usually, initially they will make a big size, then slowly when it is reaching to the minimum, then they reduce the learning parameter size. The gradient descent algorithm is repeal. So I'm not going to discuss the full derivation of that. Mathematical gradient descent algorithm will give us these equations, theta naught and theta 1, j equal to 0, 1 here. They can be found by repeatedly finding theta naught, theta 1, or updating theta naught, theta 1 by using these equations. So theta j equal to the present value. Initially, this is random initial value, but later on, the second iteration will give you some theta j based on this equation. Theta j minus alpha is again, this is user parameter. You can take 0.001, something like that. Initially, you may take 0.1, but after some iterations, you should reduce that alpha. Or you can uniformly put that only will take more steps, that's all. Not damage the thing, it will become more computing intensive if you take the small alpha. So alpha is the learning parameter. Delta by delta theta j, as I told you, it is the derivative of this j theta naught theta 1 with respect to theta j. So you should also know what is partial derivatives. So partial derivative is nothing but when we are getting the derivative of j function with respect to theta j, all other variables other than j will be treated as constant. Then you will get the partial derivative. The feature index number, the 0, 1 is if you substitute theta 0, then theta 0 equal to theta 0 minus alpha delta by delta theta naught, cost function j theta naught theta 1. If you write theta 1, then delta by delta theta 1 minus delta by delta theta 1 will come. If alpha is too small, gradient descent can be slow. If alpha is large, gradient descent can overshoot the minimum or fail to converge or diverge. So as I told you, it's when you are coming close to this yellow thing which we need to land, but if you take the bigger size, means you move in that direction, then you may fall after the yellow. Then again, it's if the same size if you use, then again you may fall before the yellow. So that oscillations will come. You will never come there because your step size is big. So that's why this says that if alpha is large, gradient descent can overshoot the minimum or fail to converge or diverge. Then why don't we take only small values? What is problem with small values?
It may take more time to reach that yellow line, yellow point.
More iterations you need to do. More iterations means more cost of computing. Gradient descent can converge to a local minimum even if learning rate alpha fixed. So he says that it may be slow, but still it converges. Don't worry about that. It's so you see here theta values theta naught theta 1 here. Our present theta value to change in function value. This is tangential, whatever it's you in which direction you need to move. Df d theta is nothing but, if somebody want to understand mathematically, we are looking at how it is changing the function value with respect to theta. So small change in theta, how it results small change in the function. So if that is positive, it is moving negative direction. If it is negative, then it is moving positive direction. So that is the thing. Df by d theta is also called slope. Slope equation is also written as tan theta, right? Theta of tan inverse. So this is right triangle. In right triangle, you are getting df by d theta is the tan theta, but not this theta here, tan of angle, whatever that you are getting. So that is the slope usually. If you want, you can go back to your geometry and trigonometry, see that how it is written tangent in terms of the derivatives. How much change we get if we increase theta value. So df by d theta 1 slope, this is df by d theta naught is the theta naught slope. So slope means how much change we get if small change in theta we increase in theta 1 value. Similarly, how much change we get if we increase theta naught value in df. Our df is nothing but the change in f. If positive change in function, you should move negative side. If negative change comes this df by d theta, you should move positive side. So that is what we need to understand. Why that it's in? If df is more, when will you get negative? When will you get negative? Theta won't become right negative. Only df may become negative. Theta you are moving in one direction, right? Left, right now.
Theta positive.
So your function value reduces, then df will become, if function increases, your df will become, as theta increases, f value increases, your df will become positive. If theta decreases, your df decreases, then also it is positive. But if theta increases, df decreases, it becomes negative. So theta is increasing, but your df is decreasing, then you should move to the right direction, right? So that is what here it says. If minus change in function, then it should move positive theta. Okay, this we discussed it. So when specifically applied to the case of linear regression, a new form of the gradient descent equation can be derived. We can substitute our actual cost function and our actual hypothesis function and modify the equation to j theta equal to 1 by 2m. This is the cost function for us, which we defined just now. Then get the d by d theta naught, whatever the partial derivatives of j theta naught theta 1 with this. Then you are getting d by d theta naught of all these things. We, other than any theta naught, we consider them as constants here. Then you are getting 1 by 2m, I is equal to 1 to m, 2 of h theta xi minus yi. So then this is product rule. You know that it's a dfx by dx is nothing but first we should do dfx by df, then df by dx, something like that. So 1 by m, I is equal to 1 to m h theta xi minus yi. Then finally you'll get these equations. This h theta x we know. Substitute that h theta x, then you'll get y theta naught plus theta 1x minus yi. So that whole square, yi is constant because it is observed value. We don't change that. It is not a variable. So finally, you'll get theta j equal to theta j minus alpha delta by delta theta j theta. So you can put both equations in one form, theta j, whether it is naught or 1, theta naught or theta 1, theta j minus alpha by m, I is equal to 1 to m, h theta xi minus yi xi. So yi is treated as constant, but this is inside of the function. So first we should get 2 of this, then derivative of whatever is there in the brackets. So that is nothing but 2 of h theta xi minus yi, then derivative of this h theta with respect to xi. So if it is 0, then delta by delta theta j, theta xi minus yi here. Okay, so whenever you get this theta, they're writing it's a theta naught plus x power naught constant. Then this is 2 times of that, m is constant, then 2 will cancel as we said in the beginning as a convenient. Then I is equal to 1 to m, then 2 times of this, then derivative of this h theta xi with respect to theta j, delta by delta theta j. Then what is your h theta function? Theta naught plus theta 1x, right? Minus yi will be as it is here. So yi is constant. This won't give any positive value here. It becomes 0. So only with respect to theta, you'll get. So theta naught plus theta 1 xi, that will convert finally like this. See? Only x will remain with respect to theta. So theta j equal to theta j minus alpha by m, I is equal to 1 to m, h theta xi minus yi. How are you getting this x here? Xi? So this should be little bit expanded here. This theta will contain both theta naught and theta 1, right? So the derivative of that, so if it is theta naught, you'll get theta naught plus theta 1 xi, whatever that it's in, theta 1x. Then theta 1 is constant with respect to theta naught. That value will go, only theta will remain here. And if you consider with x, theta 1, then the first value will become 0, derivative of the first value, only x term will remain there. So that's why you are getting this xi for theta j. Yeah. Theta j equal to theta j minus alpha by m, I is equal to 1 to m, h theta xi minus yi. The previous values are also given the same for us. Here, theta j equal to theta j minus alpha of delta theta j, j theta naught, theta 1. From this only we are getting those values. So apply your mathematics and derive that formulas. Then you'll get theta j iterations. So the point of all this is that if we start with a guess for our hypothesis and then repeatedly apply these gradient descent equations, our hypothesis will become more and more accurate. Means you come close to the theta naught theta 1, which will optimize your cost function. Gradient descent for linear regression. If you want to see that it's a visually, it's a how your gradient descent they are finding, you can also find from this link. I have already shared this presentation with you. You can open this link and see that it's how actually this gradient descent change as you change theta naught, theta 1, and how you find the optimal theta naught theta 1 values. So one thing you should remember, whenever you are updating your values, you should update simultaneously. Simultaneously means theta naught theta 1. One iteration complete means both theta naught theta 1 to be completed iterations, because theta naught involves theta 1 value, theta 1 involves theta naught value. So you cannot do that only first theta naught updations, then theta 1 updations. So one unit of the iteration is nothing but simultaneously theta naught. First you should find out the same theta naught should be used to update the theta 1. That is called simultaneous. Then second time, again theta naught update, then again theta 1 update. Then again theta naught, theta 1. You cannot update only theta naught, theta naught, theta 1, theta naught with existing theta 1. Theta 1 also should be updated simultaneously. So that is what this algorithm says. Okay, this is the linear regression. As I told you, it's you have the libraries to fit the linear regression. Now you don't need much to understand how all these things. We got some understanding that there are mathematical techniques which will optimize the functions. So we converted our cost function in terms of the theta naught theta 1 variables. Once we write the cost function in terms of the theta naught theta 1 variables, we know that theta naught theta 1 are variables. We can differentiate them with the theta naught theta 1. Use the gradient descent method to find for which theta naught theta 1 you will get the cost function j is minimum. So that is the understanding of what we need. We are not going to again derive these formulas, whatever that it's in, but you should remember, if you want to write your code updations, you should remember this theta j. This is not only for univariate linear regression. When we move to the multivariate linear regression, equation will be always same, like this only. Whether you change theta naught, there will be more variables. We may write theta naught plus theta 1 x1 plus theta 2 x2. Equation will be like this only. It's theta xi minus yi xi. This xi is actually written as a vector. X naught, all those things will come here. So exactly, if you understand how matrices are multiplied, then xi is a vector, then h theta xi minus yi will become a matrix. Whenever you multiply a matrix with a vector, you will get another vector. Then all theta naughts is also become a vector, because right side you are getting a vector, left side also you'll get a vector. So vector of theta naught, theta 1, those values. So how many variables are there for x? That many thetas will be there. Means how many independent variables are there, plus 1 you will get actually. So for that plus 1, what they did, they simply write this xi, instead of the 0, they will write x power, instead of 1, they write x power 0, then x1, x2. So even if it is linear regression, we can assume that there are two independent variables. One is the constant and the second one is the x. So the constant also can be seen as a x power 0, then x power 1. So we will also see the matrix and vector setup in the next class. So then it will become much more clear. This whole equation is written as a vector of theta j that will contain theta naught, theta 1, theta n values. Then the right side also will become a vector, but to get this vector, we are multiplying a matrix of h theta xi minus yi with this xi. So xi means there are more independent variables, so more columns will come. That's why this h theta xi minus yi will become a matrix. Okay, I will stop it here. If there are any questions or anything, we can discuss now. So I'll keep this presentation some more time if you want to go back and see that it's some understanding on this presentation. Okay, if there are no questions, then People can leave to study on their own. If anybody has doubts, I will still remain here another 10-15 minutes. They can still ask.
Hello, sir.
Yes.
Sir, when we go for classification and regression. Hello, sir. Am I
Your
audible?
voice? Yes.
Am I audible, sir?
Yes.
When we go for classification and regression, what's the difference?
It depends on the problem, right? If you want to estimate value, like in stocks, if somebody want to know that whether it gives profits or not, that becomes a classification. If somebody asks that, say, how much profit I will get by investing it, then you should get a number, 10%, 20% profit you'll get. Then you need to predict the percentage, right? Means that will become a number, not the class. So it depends on the problem. What problem you are solving. Based on that, you will use the regression or classification. Regression is basically to predict a real value, not the class.
Okay. Do we need to apply mathematics in classification or what? No need, sir.
The same algorithm we will extend to classification, because it's the machine learning is mostly maths.
Okay.
So the concept is same, but here the cost function will change. Because there is nothing like the distance, right? You may say yes or no. Then how do you find the deviation there? It becomes a 0 and 1. So is it a good thing to consider 0 and 1 as a cost?
Okay.
So the cost function will change, but the mathematical setup, whatever is there, that will be same. So for most of the algorithms, the important thing is complex part is how do you define this cost function? Once you get the cost function, the mathematics is simple. How do you optimize that cost function? Then use the gradient descent. Most of the machine learning algorithms will use this gradient descent. So the crux of the algorithm is nothing but finding the cost function. So classification cost function is not that easy, because there are only classes are there. Then how do you say that how much it is deviating? Either it says yes or no. Here number is always good, right? You want to get 30, then you are getting 20, then you can say that my distance is 10. Almost I am close. If you say 28, then you say I'm close. But there, your right or wrong only will come in classification. You predicted right or not. There the cost function will change. The definition, what should be the cost function, what are the implications of that cost function, those things we need to see. But once you fix the cost function, mathematics is same. Use the gradient descent and fix the parameter so that that cost function will become less.
Thank you.
Hello, sir. Sir, actually, could you please share this recording this once this call is done?
I didn't get you.
No, sir. Today's class recording, sir. Please
Yeah,
share
it takes
with
time
us, later on. Yeah, sir.
Yeah, it takes time to put into the YouTube. Then they will they will process it by the evening.
Sir.
Yeah.
Sure, sir. Thank you, sir.
Sir, just got a doubt in one of the slides, sir.
You want slides to?
Yes, sir. Near linear regression with one variable, sir, not the gradient descent, near the hypotenuse functions.
This one?
While declaring no, sir. Well, we are declaring the hypotenuse function.
This is hypothesis. It's theta x, theta y.
Next, sir, we are just giving the assumption values.
Assumptions.
This one? Here, sir. Yeah, it's this one, sir. So here, the hypotenuse function, the equation is theta naught plus theta 1 of x, right, sir?
Yes.
So here we are taking theta naught as 2 and theta 1 as 3. Then how we got 2 plus 1.2x? As we have theta 1 as 3. That's my doubt.
It's a mistake. Theta 1 should be 1.2.
Okay, sir. That's
a mistake here. No. It's a mistake here. First, I might have thought 3. But when I are computing to put the numbers low, I might have changed it to 1.2. Here I did not change to 1.2. See, to make it easy, say get the numbers small, right? Then bigger. If I can take 300, then all these numbers will become big.
Yes, sir. And
Yeah, you are right. Thank you.
basically,
Anyway, this theta 1 should become 2.
1.2.
Yeah, 1.2.
And
Theta
one more
naught,
dot.
1.2. Next. Yeah, go ahead.
And here we have discussed two methods. Like in first one, we will be estimating theta naught and theta 1, and in second method, the gradient descent, we will automatically update with the theta naught and theta 1. So here it is like continuously we will estimate. So for example, first time I'm imagining as a theta naught as 2 and theta 1 as 1.2. I'll just get an answer. Again, I'll take some random numbers for theta naught and theta 1.
Only first time you will take random numbers. Next time onwards, you use these formulas, right? Iteration, updating
Yes, sir.
iteratively.
Yes, sir.
Then you may fix, I need 100 iterations to be performed, or theta naughts, whatever that updation is happening, that is the difference is very small, which I don't consider as a small as there is difference. Something like you say that it's the next iterated values are very the next iterated values and present values difference is 0.0001, then I'll stop.
Okay.
You can have two stop conditions. Either you can say do 100 iterations, then it will do 100 iterations, whatever values. You can say iterate till the successive difference is more than this.
Yes. Thanks.
Sir, we are not able to access this PPT, sir.
No, you can access if you have MSIT program.net account. No?
Even I am not able to access.
We are opening with MSIT only, sir, but it is not accessible.
All of you are. Can anybody is able to open this?
No, sir. All of us have the same problem.
No, sir.
Huh? It should. I don't know. It's a public link I put.
I think better to check it once.
Okay. So share somebody's screen and show me why it is not. So first let me verify it, what I did. It is here, 2021. Univariate lecture, right? I took here, get link, then restricted, okay. Here we will put msit.program.net. And see now, will it open?
Yes, sir. It opens.
Yes, sir.
Sir, we don't have access to the GNT.
The same thing, right? When Slack, okay.
So we're actually not in the Slack group, so we don't have that link with us.
Hemant, can you connect JNT students also to the same Slack so that they don't miss out whatever we announce in Slack or we put resources in Slack? Hemant?
He is not on the call, sir.
Okay. So who is JNTU here for this data science?
Mohan, sir.
Your mentor is also Mohan, CR is also Mohan?
Yes.
Okay. Mohan, you know Hemant or not? Who created this data science group in Slack?
I think Hemant has
Hemant.
created,
Sir,
sir.
actually, this is a triple IT. Only they have added triple IT students, I think, sir.
Okay, but is it possible to add JNTU students to this group?
If they are in that Slack account, maybe we can, sir. I don't know whether they are in that Slack account or not.
Sir, I think we have logged in with a different domain into the Slack, sir.
Mhm.
I mean,
Like-
the IIIT Hyderabad has separate domain.
Yeah,
Slack,
different
right?
domain, sir, and I think JNTU people has a different domain. So we are not able to access their names. It is not possible for us to add them. Rather, they can have one mentor from, I mean, or a representative from their side.
Mhm. But anyway, you talk to Hemant so that it's a Mohan. What can be done for this?
Yes, sir.
Either somebody has to post the everything, whatever posted here on JNTU Slack, or you need to find out a way that it's a. Can you access this IIIT Slack? Maybe there are some administrative issues or placements, all those things. They may not like this IIIT Slack to be used at JNTU because they have some restrictions on placements. They shouldn't say outside, whatever that is.
Instead, we can create a new one, sir, as we did in big data.
Okay, big data, yeah, you can create a new one and then give that it's a data science for both centers as a group. There we start posting all these things, putting your videos, your doubts, all those things. So you work with Hemant, Mohan?
Yes, sir. I'll work with him, sir, and I'll be in touch with him. I give my number for 2 more here, sir, so that I can contact them in WhatsApp and then we'll call up.
Okay, okay.
So if you don't mind for now, can you share that PPT link in the chat?
In the Slack, right? Already.
No, sir, in
today-
the Zoom chat now. As the JNTU people are not in Slack yet.
Okay, okay.
Yeah, we got it, sir. Achyut shared it.
I shared
Thank
it.
you.
Okay. Yesterday's video also somebody can share that.
I'll share it, sir.
Okay, thank you.
And one small doubt, sir, in the PPT itself.
Okay. PPT. Yeah, so
Yes,
you
sir.
want to be PPT. Okay, where is PPT? Yeah, here it is PPT.
Yes, sir. Sir, we did, as we discussed, that this line is passing through a point. It is not possible to pass through each and every point, right, sir?
Yes.
So in this case, in this particular case, we are taking difference of a single point to calculate deviation.
Not single point, all points, right? Finally, we said average deviation for each point.
Yes, sir. How we got this average thing, sir? Like
We divided with 2m, right? There are m points.
yes,
we
sir.
took
And
the
initially
error.
we measured this deviation as 4, right? I think not this
For that
slide.
point.
Can you please move to the previous slide? We measured that the deviation is of 3, right?
No, we measured as 4 right here by using this equation. We got 4 deviation, 2 deviation, 2 deviation, like this. This 3 is a mistake. This 3 should become 1.2 here. I don't know why it is not changing. It is not allowing me to change this.
Okay. So we are measuring the deviation from that actual values.
Yeah, actual value for each point.
And actually, if we change the slope or if we change the line, I mean, this 3 points can be into the single line, like for example, this 25, 35,
Yeah,
and
these 3 will come on a single line, but remaining
we
points will become far more distance, right? This will come down, right? This line, if you want to go through these 2 lines, then this makes more error. Then this also may make more error. This is on line that will become out of the line. So we need to try all the combinations now to get average mean square error less.
So after doing all this, we are saying that this line is having less deviation. Sir.
That is what the program says now. This is this line is computed from this program, right? I pasted here the program which we.
Yes, sir.
So for this
So this-
data set, this is saying this is the best.
Oh, okay, sir. And next slide, sir. And we have seen that j of theta naught comma theta 1 in that graph thing, sir.
Yeah.
15, sir. 15. Slide number 15, sir.
Yeah.
Yes, sir. Sir, how the scale is actually measured, sir?
Which
Here we
scale?
have a difference of 2 and we have a difference of 1 on this side.
Now this is a general picture here. You have two variables, theta naught, theta 1. Based on this, you are getting j theta naught, theta 1 values, right? As you change theta naught, theta 1, like earlier, you should compute the first j cost function.
Yes,
There is
sir.
a formula for cost function, right?
Yes.
So see the where that cost function. This is the cost function. J
1 by
theta
2.
naught,
Yes,
theta.
sir. Yes, sir.
So by that, you will compute the cost. That cost you are putting in z direction. So if you change theta naught, theta 1 values, it appears like this. That is what we are saying. So you take theta naught, theta 1 different values and plot them. I don't know, Python has 3-dimensional plots, then you need to explore. So if you have 3-dimensional plots, I think it is there in Python, you can change theta naught, theta 1 and compute by writing small program what is this cost. Then plot them in here like this. See? Then you'll get the
Okay. This
plot
is
like
this is plotted in which I mean, in which platform, which software? Sir?
This might be MATLAB, it looks like.
Oh, yes, sir.
But in Python also you may get 3D plots. I never did that. Because plotting is only to understand the things. Most of the times we explain with the 2-dimensional thing.
Yes, sir. 2-dimensional is we have seen so far.
Yeah. So in Python, can anybody see? I'm not getting other thing.
And one last out, sir. We consider the square of errors, right? So the square of the deviations that we are getting, right? And we
Yes.
said that that is better for
To apply
I mean,
to apply
yes, sir.
mathematical formulas. Because the absolute value also you can take, but absolute value will not give you the flexibility of applying mathematics.
Okay. Like as we discussed, the point is mentioned, sir. If we calculate derivative for x square, we'll get 2x. So
Yes.
2 and 2 will be cancelled. We'll get the value in terms of x, right?
Yes.
If we take the direct values, the derivative of direct x will give us constant, no, right, sir? So we will not have x in that.
Which one you are talking? Yeah.
Uh,
This is our j theta
yes,
naught
sir,
theta
yes,
1.
sir.
Okay.
If
Then
we
you can
calculate
take
derivative for normal x, sir, coefficient of x, for example, 2x or 3x, we'll get the value as 3, right? Derivative of 2x is 2, sir,
Yes.
with respect to x.
No,
So
we
we'll
are
have
not.
constant value.
No, we are not computing the y derivatives. Remember, y equal to theta 1 plus theta naught plus theta 1. We are not computing y derivatives. We are computing j theta naught theta 1 derivatives. So cost function derivatives with respect to theta naught theta 1 we are computing because we need to optimize this cost function. What are the parameters for cost function theta naught theta 1? So there is mathematical technique to reduce this cost, then find the derivatives of this cost function with respect to theta naught theta 1. So this theta naught theta 1, when you are defining the cost function, you can define absolute deviation like this original value and how it is deviating, whether positive, negative, we are making positive there. So it won't cancel out. But when you are doing this absolute, if you want to find out by using the gradient descent, means get the partial derivatives like theta naught theta 1, partial derivatives of j, then this absolute function is not differentiable. That has problem mainly at x equal to 0. It will become -1. It's a left derivative. If you're of mathematics, then you should understand left derivative and right derivative should be same. You might have seen in the beginning, right, how derivatives are computed, small change as limit delta x tends to 0, delta x by delta y, all
Yes,
those
sir.
things.
Yes, sir.
Like
Limitations.
so this,
There are
yeah,
limitations.
limits. So this mod function, absolute function, is not derivable, differentiable.
Okay. That means practically we cannot do that, sir. For absolute thing, we cannot calculate derivative.
You can do it, except at 0 it is not, at other places it is differentiable. But again, you need to condition, write the many conditions there. If it is 0, then don't do differentiation. If it is not 0, all those things will come. See? So that's why it is easy. See, whether you make absolute value less or squared value less, you still get the optimum at theta
Hello.
naught theta 1. It is only
Mohan.
mathematical convenience. But
Mohan,
you don't get
message చేశారు ఇందాక జయప్రకాష్ బిగ్ డేటా సారీ డేటా సైన్స్
Can you mute?
నేను ఇప్పుడు ఒక
I
టెస్ట్
got
కోసం
it,
నీకు
sir.
ఒక లింక్ పంపించాను.
Thank you,
అది మన జూమ్ లో.
Can you
సార్
mute it?
జాయిన్
sir?
స్లాక్ లో.
No, individual charts, please mute. No?
Sir,
who was asking this?
Sir, I got it,
discussion?
sir.
Okay. Yeah, this, see, you will get the theta naught theta 1 won't be changed based on whether you take this cost function or this cost function.
Yes,
Because
sir.
whenever you get the cost is less for absolute value, when you make square also you will get less only. Because you are magnifying that solid. See, if not square 3, if you make square 9s, then theta naught theta 1 only will give you that 3 or 9.
Yes, sir.
So in fact, you can say that it's in brackets you put mod, no problem. Then you are, instead of taking the normal values, you are magnifying them, that's all. See, when you magnified, your minimum value is more, but the point where you are getting minimum will not change.
Will be same. Yes, sir. That's it, sir. Thank you, sir.
Okay, then again we will see, we'll meet tomorrow. Yeah, I also pasted, if somebody is interested only to continue in Python, somebody worked out the whole course in terms of the Python. You can also, it's not a difficult thing. Python is also close to Octave MATLAB in many respects. So if he is asking to write in Octave, you can also write in Python. I don't have any problem if you use whatever programming language you want.
Sir?
Okay. Yes.
Sir, just a minute. Sir.
Yeah.
Sir, I pasted one Slack link in Zoom chat, sir.
For me.
This is a common for JNTU and IIIT guys. Data science specialization.
Did you join all the people there?
Just now created, sir, and I also informed to Mohan to join all JNTU students also.
Okay.
So I think better to you can also join the same group, sir.
Let me see.
Continue with the Google. That's okay, sir. Create account.
The account is there already, right?
Yes, sir, but it's different from MSIT.
This is different, yes, sir. This is not related domain, no, sir. That's why it will ask.
This is like how we have created for
big data.
Okay, did it come now? What is it?
Yes, sir. DS. You can see the DS. Slowly, all guys are joining.
Yes. Okay. So here I will already, the remaining things, whatever is already pasted, please paste here. From
Sure,
now
sir.
onwards, paste it here. Right. Thank you. Yeah.
Okay, sir.
Sir,
Yes.
I have one more doubt, sir. Like in previous exam, I have just come through one question, sir, which is related to gradient descent. The question is, he gave an equation y equal to something like 5x plus 3, and he gave learning rate as 0.1. He asked us to find the next upcoming x value.
No, they gave some equation. Then
They gave an equation like y equal to 5x plus 3 or 3x plus 5, and he gave learning rate as 0.1.
Okay.
Using gradient descent, we need to find next upcoming x value.
Okay. Mhm.
That's your question, sir. The whole question. He
Yeah,
didn't
the
give
same
any
thing,
data.
you are updating that theta naught, that equation is there, na? Theta j equal to theta j minus 1 by 2m sigma of x theta xi minus. That equation you need to use. That alpha is there, that is the learning parameter.
Yes,
That
but
alpha.
he didn't give any data, sir, like x and y data. He only
No,
gave
X
this
and
data.
Y data is important for that. See, how do you get the cost? Cost is based on that data set.
Yes, sir.
You know, you
So
should get.
he didn't even ask us to find the prediction. He asked us to find the upcoming x value, not the y value.
No, X values is, they should give X values, right?
Yeah, but I don't know,
X is
sir.
the
It was
independent
like
variable.
a theoretical question. I didn't even ask us to solve
You know,
anything.
theoretical questions are there many, but we will discuss at the end of this. It's saying people may ask always, will you get the same solution if anybody run this linear regression? You may not get the same solution, but we'll get optimal solution for linear regression, that is sure. For other algorithms, there is local minima problems will come. But for linear regression, it is not absolute convex function, but it is a convex function. So it has not such problems of landing in local minima. Those are the theoretical questions people will ask. Actually. That we'll discuss once we understand these algorithms.
Okay.
So,
Yes.
Is it a placement question?
Yeah. Yes.
Blaze, right?
Yeah, Blaze.
Okay.
yes,
I noticed.
I don't know. Actually, you should get the exact question. Actually, if you come with the
Yes, sir. But
I
data is
don't-
not given, sir. I'm sure about
Data is not given, sir.
Okay,
And
data is not.
he has x value for sure. He has x value for sure.
No, X may be for him the dependent variable. If he change that, X and Y are convention, right? We are always using Y for the dependent variable. I don't know. See whether if he represent dependent variable as X,
Yes, sir.
then he may ask X value.
Yes, sir.
But X value is not related to the learning parameter. Learning parameter is only to optimize the theta 1, theta naughts.
Yes, sir.
Okay.
Thank you, sir.
Okay.